Hello and welcome to another homework helper video. This one's for section 5.3. This is sort of a repeat of the last one. The only difference between this problem and the previous one is that this time they're designating the area as a definite integral, but the idea is still the same. We're still looking for the area under the curve of this function, and we're going to use that limit definition. Okay, so it's the same process as the previous one, but it doesn't hurt to see this over again. So remember, to find the area under the curve, what we are going to do is evaluate this limit. We've got the limit as, ooh, I don't like that. I'm all crooked. Hold on one second. We've got the limit. Oh, let me get in the right place here. One more time. We've got the limit as n approaches infinity of the sum from the first rectangle to all of the rectangles, right? Remember, n stands for the number of rectangles. So we're going to add all these rectangles together, and then we're going to take the limit of the area as n approaches infinity. And to get that area, we multiply by the height of each rectangle, which is designated by f of c sub I, times the width of each rectangle, designated by delta x, right? So very similar to what we did last time, but there's a little twist in this one. So delta x. Delta x is supposed to represent the width of each of the subintervals, right? We have the entire interval where we're trying to find the area under the curve, and then the subintervals are all our smaller rectangles, right? Designated by all our smaller rectangles. So with delta x is the width of all of those rectangles that are approximating the area under the curve until we take the limit as n goes to infinity. So delta x is the width of each rectangle, is how you want to think about it. And the formula we use for that is b minus a over n. B being the right endpoint of the interval and a being the left endpoint, right? Those are x values. So in this case, we're going from -2 to 1. So this would be 1 minus -2 divided by n, which comes out to be 3 over n, and that makes sense. The width of our entire region is 3 units, right, from -2 to 1. And if we have n rectangles, then the width of each rectangle is going to be 3 divided by n. All right. So the next thing we do is have a formula for all the x values. And we're using the right endpoint method. We're finding the right endpoint of each one of these intervals, the little subintervals, and that's an x value, right, as we move along. You can tell it's an x value also because we're putting it into the function here. But the formula we're going to use for that is a, the beginning of the entire interval, plus a width. Now this would be the first endpoint. If I did a plus the width, that would get me to the right endpoint of that first subinterval. And I'm going to put an I here, and that I just keeps track of which interval we're on. Oh, excuse me. I always do that. Okay. So when I is 1, this will be the first right endpoint. When I is 2, you'd start at a at the beginning and move 2 places over, right? 2 widths over, and that would give you the right endpoint of the second interval. And for the third one and fourth one, etc., etc., etc. In this case, a is -2. Oh, I shouldn't have put 3 over 8. Let me back up. This should, I'm getting ahead of myself. The formula should be a plus delta xi, right? So for each interval, you're using one more delta x. You're using one more width. Okay, so then when you substitute it in for this question specifically, you get -2 plus our delta x is 3 over n I. So I was just putting that 3 over n into the formula a little prematurely there, right? Getting ahead of myself. Okay, so that's our formula for all these x values. But we're not exactly interested in the x values. What we want out of this f of c sub I is the height, right? So we get the height by plugging that formula for those x values into the original function up here, right? 2x squared plus 3. So f of ci is just that. It's 2 times x squared, and our x squared is the c sub I, so we're going to put in -2 plus 3 over n I squared, so that's 2x squared, 2x squared plus 3. Right, so that's merely function notation. We're taking this expression and putting it into the function for x. I'm going to simplify this now. You could put this function here into the limit definition for c sub I, but if you can simplify it first, it makes your life easier. There's a lot to write here with the limit notation and the summation notation, so it's easier just to simplify everything as much as you can before you put it in to the sum. So I'm going to do that a little bit here. First thing to do is to square this binomial, so I've got 2. Negative 2 times itself is 4. Keep in mind, we're going to multiply negative 2 by 3 over ni twice, right? So you get negative 6 over ni, but there's going to be 2 of them, so I'm going to have negative 12 over ni. And then multiply this one by itself, right? So 3 times 3 is 9, n times itself, n squared, I times itself, I squared, plus 3. If you didn't like that stuff, what you might do is write this out twice, right? You're multiplying it by itself. That's what it means to square it. So write it twice, and, you know, for those of you who love FOIL, just FOIL that out, and you'll get the same thing I did here. Next, I'm going to distribute that 2. So 2 times 4, 8. 2 times 12, 24. And 2 times 9, 18. And the plus 3. So putting your terms together here, we've got an 8 and a 3, so I'll write that as 11 minus 24 over ni plus 18 over n squared, I squared. Okay, so that's C sub I. I'm sorry, f of C sub I, right? So we've got that down. I'm going to put them into the actual limit now. So I've got exactly what I need. I'm going to put the limit of the sum of all this good stuff. So C sub I, f of C sub I is 11 minus 24 over n I plus 18 over n squared I squared. And then my formula tells me, okay, so that was f of C sub I. Now I'm going to multiply that by delta x. Delta x is what we figured out first here, right? It's 3 over n. Great. The idea is if I evaluate this limit, then I'll find the actual area under the curve from negative 2 to 1. Notice that I'm not putting the specifics about the limit and the sum here. I just assume that they're the same as they were over here. Anyway, I'm going to simplify this a little bit. I'm going to multiply through here, distribute the 3 over n to all 3 of those other terms. So we've got the limit of the sum of, let's see, 3 over n times 11 would be 33 over n. 3 over n times 24 over n I would be, let's see, what is that? 72, I think. 20 and 12, yeah. 60 and 12 gives me that. Oh, n squared, right? Because it's n times n down there. Good. Oh, sorry about that. So n squared here. And then plus 18 times 3 is 54. N squared times n is n cubed. I've got the I squared there as well. Okay. Now here's where the summation formulas come in. We're going from I equals 1 to n, right? So I'm going to use these summation formulas right here to evaluate each one of these terms. So I've got the limit, and now that I'm using those summation formulas, I'm not going to write the sum notation anymore. I'm actually performing the sum right now, so I don't need this sigma here anymore. Keep in mind that 33 over n, as far as the sum is concerned, is going to be the same every time, right? What's changing every time we evaluate each term in the sum is I, right? I is changing, but n is not. So 33 over n can be considered a constant, and the constant rule says, well, whatever constant you have in there, you just multiply that constant by n. So the constant in this case is 33 over n, and so I multiply that by n minus. For this term, 72 over n squared is a constant multiplier, right? It's like a coefficient in front of the I. And the I has a nice rule. I'm just going to use this form of the rule right here. It's n squared over 2 plus n over 2. And then, again, 54 over n cubed is a nice constant as far as the sum is concerned. And then I have a nice formula for I squared. It's this one. N cubed over 3 plus n squared over 2 plus n over 6. Great. So now I want to do the limit of that as n approaches infinity, right? So I'm not going to do that part yet. I'm going to simplify what I've got so far. So 33 over n times n, relatively simple, just 33. The n's cancel out. Minus. All right, 72 over n squared times n squared over 2, right? I'm distributing this to both terms here. So in this case, the n squareds cancel out. Negative 72 over 2 is negative 36. For the next one, 72 over 2 is again another negative 36, but there's an n left in the denominator because I have n squared and n, right? Plus, Here again, the n cubes cancel out. 54 over n cubed times n cubed over 3. N cubes cancel. 54 divided by 3 comes out to be, I don't know, what is that, 18? Yeah, 18 plus, okay, 2 goes into 54 27 times. N cubed in the denominator, n squared in the numerator, so just an n left there. One more. 54 over n cubed times n over 6. 6 goes into 54 9 times. And I've got an n squared in the denominator because I've got n cubed down here and an n up there. All right, we're almost home. Now doing the limit, now that we simplified all that, keep in mind that whenever you have a constant over the variable and n is going to infinity, that variable is going to infinity, that term is going to approach 0. So that one just goes away. Same thing with 27 over n. Same thing with 9 over n squared. All those terms go to 0. So all I have left, and I don't need the limit notation anymore because I just evaluated that limit. This constant's going to be 33. It's going to stay the same. Got another constant term here. Oops, not 6, but 36. Plus 18. Add all those together. What do we get? Negative 3 plus 18. 15. Perfect. So it turns out that 15 is the exact area under that curve. I do want to show you one more thing. Oh, just keep in mind that in the in Blackboard, in our Blackboard site, there is a video for the section 5.3 that shows you how to evaluate this on your calculator. So you want to watch that video because after doing all of this work, you can just quickly on your calculator enter in this definite integral, and the calculator should tell you that the answer is actually 15 if you do that right. So make sure you watch that video too. I hope this is helpful. I know this process is long and tedious. You can see how careful you have to be and how complicated this can get. I do think it helps to understand what you're doing as you go through there, right? Understand why you're finding delta x and c sub I and f of c sub I and why you're taking the sum and why you're doing the limit. I think that helps you through the process. Please, please, please email me if you have questions about this.